Continuous probability is the last part of the probability course. It's changed in 2020 as well. So chapter 15 is not going to form part of the assessment, but I am going to have a quick look at exercise 15A to talk about what a continuous random variable is before we get to the very specific continuous random variable that will be assessed in 2020. So what is a continuous random variable? It's one that can take on any value in an interval of the real number line. Now, that's different from what we've seen in discrete, because our random variable can take on these values of x, but x in discrete random variables will be like 1, 2, 3. The chance of success, 1 success, 2 successes, 3 successes. The chance of getting 4 or more successes. But note that we didn't ask at any point what's the chance of 1.5 successes, 1.5 successes, because it was either successful or it wasn't successful. You can't be half successful, okay? So that was the nature of discrete. But with continuous random variables, what we can do is actually get the probability that the random variable equals a value where x is equal to 1.3248 or something like that. So that's allowable with continuous. So it's often one that's measured, such as height, length, and time. So we could be looking at heights between values, etc. What's the probability of finding someone on a basketball team between 1.78 meters and 1.82 meters, etc. Continuous random variable has no limit as to the accuracy with which it can be measured in theory, but is often limited by the instrument measuring, such as a stopwatch or a ruler. So a stopwatch measures things, it measures your time to the nearest hundredth of a second. But if I really wanted to measure it accurately, I'd have to, I could use more like laser gear and all that sort of stuff. Same with ruler. Like if I'm measuring heights, I actually can't, and this is what this sentence says here, a random variable cannot take an exact value since it's always rounded to the limits imposed by the method of measurement used. So can't get exact height. All right, so if one of you guys in class said, Mr. Miller, I need my exact height, can you just measure up or measure me? I would say, no, I can't do that. I can get you a 2 decimal approximation or to the nearest centimetre, perhaps, 1.70 metres or something, but I can't get you your exact height. So the probability density function of a continuous random variable x is a function, f of x, with a domain or set of all real numbers, so that the probability of x lies in the interval AB is given by the area under the curve. And amazingly, this is where the crossover between calculus and probability comes in. So this is what a probability density function might look like. This is an example of one, okay? And what we've got is the density function here, and the probability that the random variable takes a value between A and B can be calculated by just using integration. We just find the area under the curve. And whatever that area is, in this instance, it looks like maybe 0.8, that's our probability. So the probability that the random variable is between A and B, in this case, equals, roughly 0.8 or whatever it might be. So it's the area of the shaded region. All right, so continuous probability density function satisfies the following two properties: that f of x is greater than or equal to 0 for all x values, i.e. the graph of f of x lies on or above the x-axis for all x values. So we don't get that issue of like a density function having stuff down here, okay? It doesn't work like that. Right, and if I integrate the function between infinity and negative infinity, then what I'm going to get is always going to get an area of 1, okay? And that's because when you add up all the probabilities underneath this curve, we're going to get a value of 1. Now, again, note that that's going to be different from the discrete probabilities that we were looking at. So if we had like 0, 1, 2, 3, 4 or something, we were getting things that look like this. So right, so that was our graph for discrete. And if I added up that, and that, we got the answer of 1. So the same goes here. All of these things under the curve, when I add together all the probabilities under the curve, I'm going to also get an answer of 1. Now note that the probability that the random variable equals, if I go for a specific value, so just say I try to work out what's the probability that whatever this value here, let's just say that that's 5 or something like that. So if I go probability that x equals 5 in this case, that equals 0. Now remember, with integral calculus, if I try to work out the area along one line, remember what it does is these little rectangles here get infinitely small, okay? And so we say actually the line itself, or on 5, that the area is actually 0, right? So what we note then is if I'm looking for the probability that the random variable is less than a particular value, it's also the same as if it's less than and equal to. It doesn't matter which one you use, okay? So this operation here does not matter. So I think that that's enough of an introduction to continuous random variables. Now let's go to what we're doing this year. One particular type of continuous distribution is the normal distribution, and it occurs frequently. Many things are normally distributed, and this is an example of a normal distribution curve. So what happens is that there's lots and lots of values around the mean, okay, getting fewer and fewer and fewer as I move away from the mean to the right and left. And an example of this would be 100-meter sprint finish times at our athletics carnival. We might get a mean of 15 seconds, but you're not having a go, but like someone might run it and get like 18 seconds perhaps, let's just say. But we also might get someone who can run it in 12 seconds, okay? But we might get relatively few who can do this, and then most of us are clustered around the mean here of 15 seconds, with some of us not being that good. I would have been in this category, just for the record. All right, so the notation used. So if we know we've got the normal distribution on our hands, what we can do is define the random variable as n, normally distributed. What we do is we put in the mean, represented by mu, and the not the standard deviation, the variance. Okay, so sigma squared. So we put the variance in there. And the simplest form of it is this. I think it's called the standard. Standard normal distribution is represented by this particular function here. So what I'll do is I'll just pause the video and whack it into GeoGebra and give you a look at it. Okay, so this is the standard normal distribution. Okay, so you'll notice here that the maximum value occurs when x is equal to 0. And what we've got is it's symmetrical, okay, with the values basically tending towards y equals 0 as x approaches, or as x gets beyond 3. And same over this side, I'm expecting, negative 3. So that's what it looks like there when I graph that particular function. All right, so some properties. The normal probability distribution is characterized by a bell curve. Okay, so you might have heard the bell curve before, which is symmetrical about the mean. It has a particular equation, and this equation here is based on this. But what it does is it looks at the standard deviation and the mean. And what it will do is change the bell curve to have a mean of whatever you want. So if you want to have a mean of 1.8 meters tall in the case of, say, a basketball player, and a standard deviation of 0.2, you simply plug those values into your formula there, and it'll change the normal distribution curve to look however you want. From the graph, we get a maximum value of 1 over the square root of 2 pi times sigma when the x value is the mean. Now, how does that work? If the x value is the expected value, then this becomes 0. 0 divided by this is 0. 0 squared is 0. 0 multiplied by this is 0. E to the 0 is 1. 1 multiplied by that is just that thing there. So that cancels out if x is equal to the expected value, or the mean. For the normal distribution, the mean, mode, and median are the same. Many of the frequencies are situated near the mean, so you can see there that lots of these things happen around the mean. The graph extends indefinitely to the right and the left of the mean, but it never touches or goes below the x-axis. That is, this thing's got an asymptote at y equals 0. And the area between the normal curve and the x-axis is always equal to 1 square unit. That is, if I integrate the normal distribution function between negative infinity and positive infinity, the answer is going to be 1, because all of the probabilities under the curve will all add up to 1. And I can also get probabilities between certain values by integrating between those values. So you can get probabilities between, if you're looking at basketball players, between 1.8 and 2.0. The probability that the height is between 1.8 and 2.0 simply by integrating. So onto the standard. So the standard is the basic normal distribution curve, which hasn't had any transformations done to it. And it has a mean of 0. So you can see here, got a mean of 0 and a standard deviation of 1. Now I'll talk more about the meaning of standard deviation, but it's got a standard deviation of 1. That's all you need to know at the moment. Because it's the simplest form of the normal distribution, it's given a special name, the standard normal distribution. And yeah, it's shown to the right. And if we reflect it in the y-axis, then we get the same function again because it's an even function. Okay, so the probability density function is symmetric around 0 because when I try to reflect it, I get the same thing in return. So we denote the random variable of the standard normal distribution by the letter Z. So remember, this one here is a very specific normal distribution. So we looked at X being normally distributed with a random variable, which was the expected value, mu, and the variance, sigma squared. So that's how I defined a normal distribution that's not the standard. But when I've got the standard, my random variable is Z, which is normally distributed with a mean of 0 and a variance of 1. Notice it says here in the notes that the standard deviation is 1. That's because sigma squared is 1 squared. Okay, so note that when I'm actually writing it like this, that's going to be sigma squared, or 1 squared, which is equal to 1. So I can write it as 0, 1, but just note that that's going to be the variance there. All right, we'll talk a little bit more about transformations later on, but if we want to map the curve of the density function of a normal distribution with a mean and standard deviation to the standard, what I do is I use these transformations here, and what that will do is take any curve that I've got. Say I've got a curve that has looks like this. It's got a mean of 20 and a standard deviation of 2 for argument's sake. If I want to get that curve back to the standard, all I do is I do these transformations. Now, speaking of transformations, what we can see here is if I've got a mean of 0 and a variance of 0.2, what I'm going to get is this blue curve here. Okay, so centered around the mean of 0, standard deviation of 0.2. Now, what the variance of 0.2 means is that if I square root that, that tells me a little bit about how the data is spread about the mean. Now notice that this, you would say, has got a small spread about the mean. That's because the variance in this case is quite small as well, 0.2. Now notice that for the next one, we have a mean of 0, but a variance of 1, or a standard deviation this time, because I square root that, that's going to be 1 as well. And what that's going to do is actually spread out the results. And so you notice that the difference here with the red function is that we get those results there more spread out. That means that the results are more spread about the mean. Okay, we've got another one here, which is a mean of 0 and a variance of 5, or a standard deviation of, what's it going to be, like roughly like 2 point something anyway, which means that that's that yellow function or the brown function there. And what it does is just spreads it even further. Now the final one is this one here, which has a mean of -2. Now notice what that does to the function. It then centers it around -2 with a standard deviation of 0.5. So again, that's how it spreads about the mean. So if we graph the normal distribution, it's is dilated and thinner, then the height will increase and a wider graph will have a lower height. Now, why is this? Well, because the area between negative infinity and positive infinity for the function has to equal 1 no matter what. So if I spread it out more, see this red one here, it's spread out more. So what has to happen is, because I'm spreading it out more, the top value or the highest value has to come down, because the area under the curve always, at all times, has to equal 1. Okay, so if I dilate it, I have to then, something else will give. So it will always make sure that the area under the curve is equal to 1. Okay, so let's have a look at one. So on the same set of axes, sketch and a calculator can be used to help the graphs of the standard deviation or the standard normal probability density function and a graph of the probability density function of normal distribution mean of 1, standard deviation of 1. Okay, so recall, let's do the first one. So I'll just draw up a quick Cartesian plane. So here is our standard. So we've got 0, 1, 2, 3, -1, -2, and -3. Now recall that our standard is Z is normally distributed with a mean of 0 and a standard deviation of 1 because the variance is 1. Now notice that the standard deviation 1 means that we get nearly all of the values within plus or minus 3 standard deviations of the mean. Okay, now what am I trying to say there? Well, I'm going to show you that GeoGebra graph again, and notice that this is the standard and it's got a standard deviation of 1. So we've got 1, 2, and 3. -1, -2, and -3. And that means that we get nearly all of the values within plus or minus 3 standard deviations. So if I was to draw this graph, I would simply go along here, start increasing till I got up there, come back down, and continue going. And it will continue indefinitely that way and that way. All right, so now let's compare that to a normal distribution with a mean of 1 and a standard deviation of 1. So notice that this has got the same standard deviation, different mean. Right, so what it's going to have is the same shape, but instead this time, what we're going to have, let's just change color here to do my next graph. We'll go red. No, axis is red. Let's go this one. So what's going to happen here is it's going to go to the same height, except this time we're going to go all the way to 4 and -2. So it's going to be, let's try to draw it. That's pretty bad. Let's try again. That's all right. So you notice there that it continues indefinitely to the left and right. What's the difference here? Notice that the mean, in this case, mu is equal to 1, whereas here mu, the expected value, was equal to 0. Now notice what's also happened. The standard deviation of 1 means that from the mean, what I'm going to get is 3 standard deviations to the left. So 1, 2, 3 standard deviations, and 3 to the right. 1, 2, 3 covers almost all of my values. Okay, and that's again a characteristic of the normal distribution. Now let's have a look at the next one. The next one says normal distribution with a mean of 1 and a standard deviation of 2. All right, so let's try that one out. So we'll draw up our axes again. So we want the standard. So let's do that first. So we got a mean of 1 and a standard deviation of 1 as well. Mean of 0, standard deviation of 1. So here comes our standard. Notice I'm not marking the max value in there, that doesn't matter. Right, so there is that curve there. Now again, notice that I'm moving away from the asymptotes, and we should probably put an asymptote into this one as well. So y equals 0 and an asymptote here at y equals 0. That's a little bit naughty of me, so again, sort of make sure you pay attention to your graphs. All right, now what they want us to do now is also sketch normal distribution with a mean of 1 and a standard deviation of 2. Here's the standard normal distribution curve here. Now what I'm going to do is pop in another one that has a mean of 1. All right, and what's going to happen is it's going to have a standard deviation of 2. All right, now what does that mean? Okay, so what's going to happen is, remember, 3 standard deviations to the left. So here is 1 standard deviation because it's 2. So the standard deviation is 2. So we're going to go from 1 to 3, to 5 to the 7. Right, so we're going to have, again, centered around 1, but instead the standard deviation is 2 this time. That means 3 standard deviations to the right is taking me up to this value here. Let's go to the left now. So there's 1 standard deviation, 2 standard deviations. Let's go 3 standard deviations, excuse the scale. All right, so now we can graph this function. Now, remember, our max value is there. Because our standard deviation is larger, that means it's going to spread the values out, which will bring down the max value. So we can't put the max value at the same height, because then we're going to get an area less than 1. Now, I'm just guessing here, but all I'm showing you is that it's not going to max at the same value. Now, let's sketch our curve. Hard to do this. All right, so that's not a fantastic effort, but it's good enough just to depict the fact that the difference between the standard, okay, drawn in purple there, and this one in violet, is that this one here, or in this case, the expected value or the mean is 1, and we've got 2 standard deviations or the standard deviation is 2, so that's going to jump by values of 2 and jump by values of 2. So it's going to spread it out, which will in turn bring that maximum value down so that it will preserve an area of 1 at all times. All right, so try that out for yourself now in exercise 16A.